I'm proud to say that I'm now Michael Knoelker's neighbor at HAO. I'm in the office next door, and I'm honored that this was on his invitation. I was previously in a windowless office, and he said there's a nice sunny one next to mine, and that's led to lots of nice conversations with Michael. And I hope those will continue as he continues as emeritus visiting. Okay, so I'm going to be talking about what we've learned about the sun from other stars. And I like to call the solar cycle the oldest unsolved problem in astrophysics. And I felt pretty confident about that until you brought up that we don't really understand star formation, and probably people have been wondering about that for longer. So maybe there's a debate in there, but I'm not going to change my talk. So I was
going to make that comment.
Yeah, but maybe we can have a debate. Maybe we can settle this. All right. And as proof of this, you just go to the Wikipedia page where you find proof for everything. List of unsolved problems in physics. It's right here, and it gives it the heading. It says that some of them are theoretical, observed phenomena, meaning that the theories are incapable of explaining certain observed phenomena or experimental result, and the others are experimental, meaning that there's difficulty in creating an experiment to test a proposed theory. And I think both of these are true in the case of stellar dynamos. And there it is, right there at the top of the list in the astronomy and astrophysics section, the solar cycle. The question is, how does the sun generate its periodically reversing large-scale magnetic field, et cetera, et cetera. The coronal heating problem is there too. And then I'll just reveal to you why you probably shouldn't take Wikipedia's page. I edited the page this week and put this up there. Actually, I edited this page in 2016 and put these in there. And the edit that I did this week was to move them. Someone had put that in the plasma physics section. And I was like, yes, it is plasma physics, but they are stars. So, I put it back in the astronomy and astrophysics section at the top because I just didn't know where else to put it. So yeah, the solar cycle is the oldest unsolved problem in astrophysics. I mean, Galileo observed sunspots through his telescope. He had a debate with Scheiner, yeah, that where are these? Are they in the Earth's atmosphere? Or are they near or on the sun? What is their nature? Now we have much better observations of sunspots, and we still wonder the same things. They come and go in cycles, but what are they, and where do they come from? It's not like we know nothing. I mean, our opening talk today tells us that we have, quite a few good hunches about the nature of the dynamo. But it's what I like to call we have unsatisfactory solutions. So we don't have what I would call a satisfactory theory of the dynamo that explains all of this variation in the solar cycle, including this remarkable change in the pattern of variation at the modern minimum. And it's interesting that we have at least one observed instance that the sun can change its patterns of variability dramatically. And as evidence that it's an unsolved problem, I put these two pieces of evidence. This is a quote from Paul Charbonneau, dynamo theorist, in a review of his, asking the question, what sets the dynamo period? It is sober to reflect on the fact that over 150 years of the discovery of the solar cycle, the mechanisms setting the period have not been pinned down with confidence. In mean field and mean field-like models, the possibility to adjust parameter values not well constrained observationally. So it's a problem, maybe if we just had better observations, we could constrain those things. It makes it possible to attain solar-like cycle periods no matter what the dynamo modeling framework is adopted. And so I would be satisfied with the dynamo theory if you gave me, if we could take mass, if we could take composition, if we could take angular momentum and say it must have a cycle, right? So sort of from first principles that. The other evidence that I give is when we go through this exercise of predicting solar cycle amplitudes, you get the community basically predicting everything. So somebody's guaranteed to be right, but it sort of indicates that that there's so much uncertainty around the problem that it doesn't cluster around the right answer at this point. And Charbonneau adds, this is where observations of magnetic activity cycles in stars could offer powerful discriminants. And that idea goes back to the Mount Wilson Observatory. A fellow named Olin C. Wilson, who started doing observations in the 60s. And he wrote in his paper that was aimed at getting cycle data in other stars a little bit about why he was doing this. So we have this solar cycle of a 22-year period, a vast amount of observational data and theoretical speculation regarding to the cyclical solar variation has been accumulated. Nevertheless, it seems very likely that understanding has been hampered by the fact that we're only looking at one star. And parameters such as age, mass, and particular parameters such as age, mass, and surface temperature, is reasonable to suppose that if analogous cycles could be detected on other stars, emphasis mine, different values of the fundamental stellar parameters, that would be of help to solving the problem. And so, work set out at Mount Wilson Observatory, which used to be called, by the way, the Mount Wilson Solar Observatory, because it was purely solar physics in the beginning, but quickly added the nighttime telescopes, the 60-inch HAO telescope and the 100-inch Hooker telescope. And I remember on the first day, I knew I was going to put these in the talk, and I was like, look at our beautiful new telescope. It makes these things look positively old, which they are. But anyway, this is where the HK project began. And the HK project was Olin Wilson's idea to measure stellar activity using emission from the calcium H and K cores, which on the sun is demonstrated to be correlated with the presence of magnetic field. So if you integrate over the surface, unlike with magnetic field where you get cancellation, you'll get magnetically heated chromospheric emission that is going to be a proxy for unsigned flux on the surface of the star. And that's through this S index, which is a ratio of the H and K emission bands in 1 angstrom to 2 pseudo-continuum bands on the side. And another version that I'll be using is this R prime HK, which basically takes the color term out of it. So if you're looking at stars with different continuum intensities, you don't want your index to be skewed by that. So then it becomes a flux ratio. So fluxes from the chromosphere in H and K as a function of as a ratio with the bolorimetric flux of the star, so that you can compare stars of different temperatures. So Olin Wilson went to work at the Mount Wilson Observatory, smoking a pipe like any good astronomer of that day. And he began accumulating observations first at the 100-inch telescope, and using a spectrophotometer, which was the innovation that made him believe that now is the time that we can actually make this possible. We can get accurate enough counts to capture these variations. And so the observations began in '66. The first descriptive paper was in '68, and in '78 he announced that indeed sun-like stars. He had a set of F, G, and K-type stars. Were varying, some with larger amplitudes than the sun, some with lower amplitudes than the sun, and one star that he thought might be cyclic, but he was very cautious because he only had 10 years of data and he only saw it go up and down once. But observations continued with Sally Baliunas after that, culminating in a landmark paper in 1995 that's basically summarizes almost everything that we know about long-term variability in other sun-like stars. It's interesting to notice the slope changes in this distribution. We reached, by the end of the program, something around 160,000 observations. And that's one measurement of on a night for a given star. Individual exposures, you multiply by a factor of 3, they averaged like that. But you see these slope changes here. One is when they moved to the 60-inch telescope in 1978. That was described by Von Preston and Wilson, and that their productivity enhanced greatly when they went to the smaller telescope, probably because they had an easier time getting time on it. And it basically continues at the same rate until the end of the program with a little blip around 1995. And I wonder about that. Was that just them writing the papers? something like that. Anyway, there's Sally. And so there's these three programs that I'm going to talk about. The Mount Wilson HK project, 1966 to 2003. Photometer counts in 2 to 4 channels of the S index. The HAO Lowell solar stellar spectrograph, so developed at HAO, deployed at Lowell Observatory on a 1.1 meter telescope. It's a mixed mode spectrograph with the H and K being observed with a litro spectrograph, and then they also have an Echelle spectrograph that gets orders throughout the visible. And that started, the time series began in 1994. It was deployed in the late 80s, and those continue to the present. And then the Fairborn APT program, automated photometric telescopes at Fairborn Observatory, measuring a different index. It's just brightness changes in the sort of medium band B and Y Strobgen photometry, 40 nanometer bands in the visible. That's been going for 28 years. If you combine the two calcium surveys, then you can develop stellar time series now of length up to 55 years, which is pretty good. Quick thing about HAO's involvement in the solar stellar spectrograph. In 1983, Dimitri Mihalis wrote a letter to Arthur Hoag at Lowell proposing a joint project on the solar stellar spectrograph, and it was installed in 88, and here's a few photographs of Dimitri there on the left, and others who were involved. There was Dick Fisher, Gilliland, and others at HAO that worked on designing the spectrograph and delivering it to Lowell. This is a really nice letter from Dimitri Mihalis where he finishes up. As you well know, I lack subtlety, and as you can see, if everything goes well, I am proposing in effect to tie up your telescope almost full time. The reason I have the audacity to propose this is that I firmly believe this is good science, even if it lacks the glamorous glitter of high-profile whiz-bang astrophysics. In every real sense, we are in a position to finally realize the grand scheme laid out down 80 years ago by George Ellery Hale. Hale, of course, being a solar physicist who also looked at things in the nighttime, maybe the pioneer of the solar-stellar connection. What do the sun-like stars teach us about the sun? So here I'm going to start a short outline. First of all, most important thing is most stars do not have a cycle like the sun. We're too fixated on cycles because that's what the sun does. But there are many patterns of variability. On the left column, we have flat activity stars that have a relative variation of 2% or less. These are classifications, by the way, from Baliunas et al., 1995. They're all time series of the data up to that time in the S index. These long-term variabilities where they have some sort of secular trend in them, or maybe a period that's longer than 25 years, so that they can't measure it too well. And then these erratically variable stars that don't have a statistically significant period of variability, but are quite variable nonetheless. And then on the right column, different classifications of cycling, graded from poor to fair to good to excellent, according to their false alarm probability. That is, that the probability that the signal, the sine wave, if you will, in the time series is due to white noise. And as you can see, as it gets very low, it starts to look pretty close to the solar cycle. There's stars with 2 cycles going on at the same time. Here's one of 17 years and 2.6 years going on rather persistently. And although it wasn't stressed very much in Baliunas 95, the claim that most stars aren't cycling is right in there in these histograms. They reported 52 stars that are of their 112 that are cycling, so it's less than half. But if you also consider that the sun's cycle isn't one of these sort of 2-period cycles with, at least with periods that have comparable amplitudes, then you can take that number down to 43. So you're at about a third of the stars that are in some sense cycling. But I maintain that it's we might be even a little more cautious than that, because the solar cycle is easy to detect in these data. All right, we're not in a challenging signal-to-noise regime. The signal-to-noise ratio, where noise is rotational variability, the amplitude of variations on the rotational time scale, versus the solar cycle amplitude is 2.3. I mean, you can pull this signal out of very sparsely sampled data. The measurement precision of the S-index at Mount Wilson is about 1%. The amplitude of the cycle, based on a paper I wrote that has some new calibrations, is about 8.6%. And so yeah, if you compare the easy to detect solar cycle to these stars, you see that it's really the good and the excellent classes that remind you more of the solar cycle, and the other ones, they don't seem to have the same characteristics. Even though they have high levels of activity, high levels of variation. If they were really sun-like cycles, I think you should see the cycle popping out at you. And so I did a work in my thesis that classified the Baliunas 95 results a little more in a more presentable way. Here I break them down into histograms, F, G, and K type stars, 3 groups of roughly equal population. The F group has roughly half of them are of the flat or the long-term trend variety. The green are the cycles, right? And you see that the G group and the F group have about 34% of them cycling. The K group has much more of them that were classified in some sense as cycling. Right. The G group was most likely to be some sort of erratic variable. Then if you look at those classifications I was just talking about, you see an even more stark difference. Those high quality cycles, of which the sun is one of them, are rare in the G group. Of the G-type stars that are cycling, there are only 3 stars, including the sun, that have a high quality cycle of the good or excellent. I should note that one of those other stars is a subgiant, so not very sun-like. It's a G-type subgiant. And the other one is a 2-cycle star. So there is only one, I claim there's only one sun-like star in the, known in the G group. Of G-type stars, there is only one sun-like star. It's the sun. And that's not true if you go now to the Lowell data. There are more examples of high-quality cycles from G-type stars. It's interesting nonetheless to know that the K group, 81% of those are high-quality cycles, all right? So if you want to look for sun-like cycles, you should be looking at K stars, apparently. 2, the rotation and stellar structure determine the level of and amplitude of magnetic activity, and the sun's activity is weak. We've already seen this, but it's shown very nicely here in the Noyes et al. 1984 work, which parameterized rotation by the Rossby number using a mixing length model, actually. And that collapses all of the stars when the rotation is expressed in Rossby number onto a single relationship with activity. So this is the activity-Rossby relationship. Here activity is expressed as log of R prime HK. And you see the sun right down at the bottom of all of the stars in this Mount Wilson sample, 41 stars. In my thesis work, I gathered rotation periods from the literature and did this for more stars, and it's nice to flip back and forth between rotation period on the x-axis and Rossby number on the x-axis and see how everything jumps onto roughly the same relationship. So if you're just looking at rotation period, it's the cooler stars with deeper convection zones for a given rotation period that have higher levels of chromospheric activity. And then when you put in Rossby number, everything jumps in. There's a lot more lower activity stars in the sun here, and the relationship gets a bit fuzzier around there, and that's interesting. So if you just look at very sun-like stars within 5% of the effective temperature, you can see not only does the activity here measured in the S-index decrease with rotation period, and the sun being among the lowest of them, but also the amplitude of the variability. These bars here indicate the inter 98% of 50-year time series of calcium H and K. So just chopping off the top and bottom 1%. The fast rotators have very large amplitudes compared to the sun. And there's a linear relationship between median activity and the amplitude of activity. That also, we also see that the sun is on the low end of the activity spectrum in terms of its brightness changes. So this is using that Fairborn Observatory APT data, the photometry and the visible bands. It's RMS variations over time series that range, I think, up to 23 years, but average of about 17 years. So they have the precision to measure millimagnitude changes in brightness changes because they're doing relative photometry. They have standard stars, and they're measuring the change with respect to those standard stars. And then they check the standards with respect to each other and make sure that they're not varying, so they're constant. So a very clever technique to achieve sub-millimagnitude precisions that's required to get something like the brightness changes of the solar cycle, which from TSI, total solar radiance, space-based observations, we know that the solar cycle is less than 0.1%. Here in RMS, it shows up lower, of course. But yeah, the sun, for its chromospheric activity level, is looking rather inactive. And there's a recent work that that we did with Phil here, Phil Judge, Egeland, and Henry 2020, now in press, using this data and an assumption. Assume that sampling a short stellar B-wide time series of sun-like stars is equivalent to randomly sampling the solar variation in time. That is that you can draw variations of the sun from a group of sun-like stars. Take that assumption. Then you can use that to put constraints on the variability of the sun over longer time series, which are interesting for climate, for reasons of Earth climate. And so the first step is to select a sample of sun-like stars, and we took these directly from the Radek paper that I was discussing earlier. Basically, it's a low activity cut, which ends up to be, it translates into an age cut, so they're all old stars, they're all low activity, they all have low amplitudes, as I showed in the other slide. You estimate a secular trend from each of these, so just take the time series and fit it using the uncertainties, and you get a trend. You take an ensemble average, and of course the average of many stars is not likely to be correlated, so it's 0. But the interesting thing is the standard deviation about that. You get plus minus 19 millimagnitudes per year. So scale that, just multiplying by 271 years to get this since 1750 standard, and convert it to units of flux, so it's something like the solar forcing. And you get a constraint based on your assumption in this set of stars of plus or minus 4.5 watts per meter squared, which is comparable to the anthropogenic force over this time period estimated in the IPCC reports. So is this controversial? I think not. What it is, it's an interesting technique using real data that has further potential to put real constraints on the solar variability over time. The other approach is to take the TSI time series and connect them to another proxy like the sunspot record, and go back and based on the assumptions and the way that you do that, you get wildly varying results. This is one that with further data you can constrain further, and I think it should be thought of as an upper limit to the variability that the sun may have exhibited in the past. And interestingly, it actually rejects some of the larger proxy estimates that have been in the literature. The third and final thing I would like to talk about is that rotation and stellar structure determine the temporal patterns of long-term variability. This is the most interesting thing for me. So here are four stars. Yeah, the sun's a star too. So the sun and three other stars, all plotted on the S-index with the same scale, and you can see what I've talked about earlier, that some stars have much larger amplitudes and much higher means, and those things go together. Both of those stars above were classified as cycling in Baliunas 95, and you can just sort of qualitatively see it's not the same kind of cycling in the sun. It's not as well behaved. It's not as regular. They don't always return to the same minimum point, approximately, over time. So whatever these stars are doing, it's not really sun-like. And it seems to be that with faster rotation period, the variability becomes more complex. And with longer rotation periods, it gets simpler because you don't seem to vary at all. Flat activity. Travis showed this, this picture of the evolution of cycle period that follows that. And so you have the sun spinning down. Sun-like stars produce the evidence trail here, spinning down. You're along this inactive sequence on the back, on the bottom. You have these multi-periodic, so the same star is appearing on the active branch, the higher one, as the lower branch, 2 cycles in parallel. And then when you get to close to this solar age, this transition point that we're investigating, the rotation period stays fixed. The cycle period continues to evolve. And I should add that this trend of rotation period, longer rotation period leading to longer cycle periods, is best shown in this K-type stars, and they're all on this right side. These red stars. This is that K group I said with the high quality cycles, the goods and the excellence that you don't have to be. I mean, you don't have to do any mental gymnastics to get the cycle period. You could just measure it with a ruler on the time series. It's very easy to do. So this is a very robust result for the K stars. So the question is, why does the sun have a sun-like cycle? And the thing it has in common with these K-type stars is its Rossby number. And that's what's shown in this plot here. So we know that this, using the Rossby number, collapses all of the stars into a single sequence according to their activity. It also puts the sun on top of all of the other K-type stars that have these high-quality sun-like cycles. More complicated variability seems to begin as you get to rotation periods faster than Rossby numbers of 1.5. That's where the multiple 2-cycle variation starts to appear in the G-type stars and the K-type stars. And then the erratic variables appear there. So these are classifications from the Baliunas 95 paper, combined with rotation periods from the literature. And so all of the green stars are sort of clustered around each other, with a few exceptions that other authors on closer analysis of those time series have classified them as complex and not sun-like as well. And so, yeah, why does the sun have a sun-like cycle? Because it has a sun-like Rossby number, I guess, of around 2. So it appears that the rotation is strongly determining the patterns of variability. More connections between cycles of other stars in the solar cycle is in this paper I did together with Bidyakarek and Garg. It finds the Waldmeyer effect. That is that a correlation between the rise rate and the peak of the activity in a cycle. So we took the Mount Wilson data, those high quality cyclers, the mostly K-type stars again. We actually fit functions to their individual outbursts of activity or cycles, if you will, and found that they have a Waldmeyer effect just as the sun does. It follows roughly the same trend, which makes you think that there's probably the same process going on. More evidence, at least, that the same process is going on. So those are the 3 most important things to take away, I think. Moving quickly along, the modeling effort that takes these stellar observations into account, I think is, well, it's rather rare that a dynamo model even uses rotation as a parameter so that you could say it, so that you do any comparison to these type of data. But those that do get the opposite behavior, let's say. in terms of they find that long rotation periods lead to short cycle periods. That is both in the mean field Babcock latent type flux transport dynamo and in these global MHD simulations, which have totally different mechanisms operating in them. One of them is sort of dependent on a tachocline and a meridional flow, and the other one is developing them in the bulk of the convection zone. Both getting it wrong in the same way. I don't know if it's a function of the authors or the publication, but they take a different reaction to this. Karak said that this is the main failure of his model, right? It had other successes. There are other things that it reproduced. Strugarek started to question the observations. So I think it may be more a result of being published in Science. He did compare the model results to observations, but in this plot he didn't put those stellar observations. So here I put them in for them, and then you can draw your own conclusions whether the trends in the models are matching the observations. Doesn't look as good. So future prospects and requirements for progress. Again, I think we've seen this phrase a few times already today. It's an end of an era somehow. All of these decadal scale synoptic stellar observation programs are going to be finished within the next 3 years if nothing changes. The Mount Wilson HK project already finished in 2003. The director of the Lowell Observatory assures me that the solar stellar spectrograph will be retired by next year. The Fairborn APT program is sort of on its last legs as well. And I don't have any firm confirmation on when this ends, but there are looming retirements that will push this thing, that will end these time series. There are ongoing HK observation facilities, but none of them are dedicated, right? And this makes a big difference in the time series. So a lot of these are exoplanet hunting facilities that sort of observe. They're looking for radial velocity changes. They sometimes go into H and K. They observe when they feel like, and if it doesn't look promising for exoplanets, they just drop it. So that's not the best way to get a long-term variability record. There's another observatory down in Mexico that's running the Tigre spectrograph. That's also has a impending retirement. On the other hand, the good news is there's a lot of archival data that's lying around. Baliunas 95 was the last, really the last word on the Mount Wilson project that continued observing for another decade. And those data were unpublished, and the fact that that only covers half of the observations at the time. There are about 150 new giants and 150 new dwarf type stars that are in this that no one's ever looked at before. And the SSS is about to publish its 25-year report on long-term variability. And the APT data needs to do so, but it's unclear whether there's actually enough person power available to make that happen. So what I think we need for real progress to improve our understanding of the evolution of stellar cycles, continue the Mount Wilson and SSS time series with different facilities to understand the long-term stability of variability patterns. We caught a Maunder minimum, once in 400 years for the sun. If you look at enough stars, you might expect to see a few Maunder minimum transitions, which could be interesting to study. And then there's just a cycle-to-cycle variation. And then let's take it to the next level. I would like to see a full sky HK survey down to 8.5 magnitude to get 1,000 suns, because like I said, there's only there are very few G-type stars with sun-like cycles, and whenever you start cutting these things into rotation bins, metallicity bins, you have one star in your bin, and there's not much you can do with that. Another option is a targeted new synoptic HK survey. We have much better ability to characterize stars before we get started. We have Gaia, we have TESS, so you can know where it is on the HR diagram before you begin. and a short activity survey can help you distribute things in rotation space to get a better sampling of sun-like stars. I would like to see 100 G-type stars evenly distributed in rotation space, and another 100 clustered around the solar activity, so that we can test that hypothesis that, that you can draw the solar variation from an ensemble of sun-like stars. And I'll just leave you with this graph. That's all.